So these are the notes for solving exponential equations. So the first one is exponential functions are equations in which variable expressions occur as exponents. The result below is useful for solving certain exponential equations. So the property of equality for exponential equations. If b, the base, is a positive real number other than 1, then b to the x equals b to the y. Hopefully you notice that these bases are the same. They can be 2, 3, 4, 5, whatever. As long as they're the same, what that means is these exponents also equal each other. So if and only if x equals y. So the small example they give us here is that 3 to the x equals 3 to the fifth. So you'll notice that the bases are the same. We can cross those out. And therefore, the exponents have to be equivalent, so x is equal to 5. And we see that answer right there. Okay, so we're going to apply that property here to these two examples. First thing I noticed about example 1 here is I have 4 to the x and 1/2 raised to the x minus 3. So what I'm going to try to do is force the bases to be the same. So 4 and 2 can both have a common base of 2. So 2 squared is 4. And now if you recall, when you have a number on the bottom and you want to bring it to the top, by properties of exponents, you can make that a negative exponent. So when I bring the 2 to the top, 2 times 1 is 2, so I don't really need that. But there's no exponent, so I assume it's a 1. But since I brought it from the bottom to the top, it becomes a negative 1 raised to the x minus 3. Now from here, we use the power of a power property, which says when we have 2 exponents to the top, we multiply them. So 2 times x is 2x. And then this would be 2 raised to the negative 1 times x, we're distributing, is negative x. Negative 1 times negative 3 is positive 3. Now we see that our bases are the same, so we can cross those out. Here I'm just going to rewrite my exponents. 2x equals negative x plus 3. I'm going to add this x to the other side. I get 3x is equal to 3. I'm going to rewrite it over here just so I can see it a little bit better. Divide by 3, and x is equal to 1. Now what you can do to test your solution is just plug it back into the original function. So 4 to the first power, which is just 1. 1/2 raised to the 1 minus 3. 4 to the first power, which is just 4. 1/2 to the negative 2. So 4 equals, the negative flips it over, and 2 squared is 4, so that answer does check out. All right, for the second example here, we have 9 to the 2x equals 27 to the x minus 1. So if you look at 9 and 27, hopefully you're seeing that the common base can be a 3. So 3 squared is 9, raised to the 2x. 3 cubed is 27, raised to the x minus 1. Once again, we're going to multiply these exponents. 3 to the 4x, and 3 to the, we're going to distribute this. 3 times x is 3x. 3 times negative 1 is negative 3. Bases are the same, you can cross them out. I'm just going to rewrite the exponents because that's what I'm solving now. Subtract the 3x, and we come up with, let's write this over here, x equals negative 3. And just to show you, I will test that real quick in this calculator. All right, so right here, I can do this in the calculator. Let's see, control minus, let's slow it out a little bit. All right, so 9 raised to the 2 times negative 3 is that. And 27 raised to the negative 3 minus 1 is that. So you notice the answers are the same, so they are equivalent. Okay, moving on. When it is not convenient to write each side of an exponential equation using the same base, you can try to solve the equation by taking a logarithm. Of each side. So in this example that we have here, I'm looking at it and I see a base of 4 and a base of 11. So I have an exponential function equals a constant. So in this case here, the problem I see is I cannot find a common base. 4 and 11 have no common base. I could try 2, but that doesn't work. 11 is just a prime number, so it's just 11. So we're going to take a logarithm on both sides. Now, the easiest logarithm to take is to look at the exponential part of your equation here. So in this case, 4 to the x is my exponential part. So I'm going to force the base of 4 to go away. So if you recall inverses, we know that, so let me give you an example here. We know that log base b of b to the x, this logarithm and this exponential function are inverses, which just leaves us with x. We can just cross those out and x is there. Also, we could have like b raised to the log base b of x. Once again, we have an exponential raised to a logarithm. Since the bases are the same, we can cross those out and my answer would be x. So over here, we're going to apply this concept. So if this has a base of 4 raised to the x power, we're going to use log base 4 on the left side and on the right side. So log base 4 of 4 to the x power, and on the other side we're going to do log base 4 of 11. So right here, they are inverses because it's a logarithm with a base 4 and an exponential with a base 4. We can cross these out, and what we're left with is the exponent of x equals log base 4 of 11. Now this right here would be an exact answer. We're going to get an approximation. So when I'm doing approximations, what I'm going to do is I'm going to do control, and right here I have a base 10 that pops up the log, and now there's a small space there for my base, which is a 4. Arrow to the right, now I type in 11. If I hit enter, it gives me the same answer, so I'm going to do control enter, and it gives me the decimal. I like to go up to it and double check that it is rounded correctly. So round to 3 decimal places, 1.7297. So 1.7297. The 7 rounds the 9 up 1, so that bumps it to 10, which in essence makes this 1.73. So my approximation is x is approximately 1.73 units. All right, for the next one, we're going to apply the same concept, same process. So I see I have an exponential, 7 to the 9x equals a constant. No common base can be found here. So I'm going to take a log base, since this has a base 7 here for this exponential function, I'm going to use base 7 on both sides. Okay, so these are inverses, so they cross out. So now I have 9x equals log base 7 of 15. I never type this into my calculator until I'm ready to get my final answer. To isolate x, we divide both sides by 9. So my exact answer would be log base 7 of 15 divided by 9. My approximate answer is going to be, let's take this and type it into the calculator here. Right here, okay. All right, so we have control divide, control base 10, so my base is log base 7 of 15 divided by 9, control enter. I like to go up and just double check it, so 0.1546, so 0.155 is my approximate answer there. All right, on to the next part. So here we're going to also solve equations again. Here this is a little bit different because the other ones just had an exponential function with a number that was a base that was a number. Here we have a base that is e. So if you recall from prior lessons that you may have seen or prior properties, here the base is e. So in order to find the inverse, we need to have log base e. But we don't actually use log base e. Instead of log base e, what we tend to use is ln. So without this e here, it's understood that log base e is a natural logarithm. So log base e, we write letters L and N. So don't get that confused with the 1, it is an L. So log base e is ln. All right, so we're going to go through the process of solving this problem here. So first thing I do is addition or subtraction. I see a -7, so I'm going to add 7 to both sides. So 4e to the negative 0.3x is equal to 20. We're going to divide both sides by 4. So e to the negative 0.3x is equal to 20 divided by 4 is 5. So to get rid of a base e, we're going to use the natural log. So ln of e to the negative 0.3x is equal to ln of 5. So once again, ln is log base e, so the e's are inverses, so we can cross that out. And we have negative 0.3x is equal to ln of 5. So to solve this, we divide both sides by negative 0.3. And x equals ln of 5 divided by negative 0.3. So that's going to be my exact answer. And let's get the approximation right here. All right. So let's take this here and plug it in. So we have control divide. Ln is second e to the x, so second e. There's my ln. So ln of 5 over negative 0.3. Control enter, and I get negative, let's go up there, negative 5.3647, which rounds it to negative 5.365. Negative 5.365. So once again, oops, let's fix that. Exact versus approximation. There you go. All right, let's take a look at the next example now. So for the next one, it's going to be the same process. We're going to add or subtract, multiply, divide, and so on. So first thing I see is subtract 9 from both sides. So now we have 3e to the 4x. 15 minus 9 is 6. From here, we're going to divide both sides by 3 to isolate the Euler, the e. E is actually Euler, if you recall. So e to the 4x is equal to 2. To get rid of that e, we do a natural log on both sides. So this cancels. We have 4x is equal to ln of 2. So 4x equals ln of 2. Divide both sides by 4. And x equals ln of 2 divided by 4. I cannot reduce the 2 and the 4 because this is ln of 2 and this is a constant of 4. So this is an exact answer. And for my approximation, so let's do control divide, ln of 2 over 4, and we get 0.173. Now once again, to make sure these are correct, like they do actually working, just plug them into here and make sure it does check out. Yeah, so you can definitely do that. All right, on to the last part here. An important application of exponential equations is Newton's law of cooling. This law states that for a cooling substance with initial temperature T sub 0, the temperature T after little t minutes can be modeled by this here. So we have T equals T sub 0 minus T sub r, e raised to negative RT plus T sub r, where T sub r is the surrounding room temperature and r is the cooling rate of the substance. So, you are cooking a licha, an Ethiopian stew. When you take it off the stove, its temperature is 212 degrees Fahrenheit. The room temperature is 70 degrees Fahrenheit, and the cooling rate of the stew is R equals 0.046. How long? I put in minutes to make sure we recall that it does say in minutes. I'm pretty sure it said it here. T minutes. Will it take to cool the stew to a serving temperature of 100 degrees Fahrenheit? All right, so the first thing I'm going to do is I'm going to find all my information. I need to know what T is, T sub 0, T sub R, R, and T. So we start with T, and T is said to be the temperature after T minutes. So in this case, it is 100 degrees. That's what we're trying to get it down to. The initial temperature was 212 degrees Fahrenheit. T sub R is the room temperature, and it says the room temperature is 70 degrees. R is going to be your cooling rate, which is 0.046. And T is actually what we're looking for, the time it takes in minutes to get the stool cooled down to a temperature of 100 degrees Fahrenheit. Okay, so now we're going to take these numbers and we're going to plug them into this formula here. So starting with T is 100 equals T sub 0, so the initial temperature is 212, minus the room temperature. E raised to the cooling rate is negative 0.046 times time plus the room temperature of 70. And we go about solving this how we normally would. So I'm going to subtract the 70. So addition or subtraction first. So 30 is equal to 212 minus 70 is going to be 142. Euler negative 0.046 times T. Just to double check that, I'm going to do 212 minus 70, which is 142. Okay. From here, we're going to divide both sides by 142 to isolate the E. So over here, I'm going to reduce it in the calculator. Which is 15 over 71. Now we take ln of both sides. Ln and E are inverses, so they cancel out. And last, we divide both sides by negative 0.046. So T equals ln of 15 over 71 divided by negative 0.046. So I'm actually going to take the approximation in time so I can figure out the minutes here. So control divide, let's see, we have ln of control divide 15 over 71 over negative 0.046, and I get 33.7963. So I think this would be appropriate to do 33 point, I'll keep it consistent, 33.796 minutes. All right, and there's the answer there. And just take a look at the work real quick.